My name is Christian Köntop. I work for Booking since 2006 or so in various ways and roles. I'm going to talk about Booking and still confused. That's better. We have been a small travel agency from Amsterdam once that ran a little website that sold hotel rooms that grew a bit over the years. Actually for, well, almost 15 years or longer now, faster than Moore's Law. So we end up today being about 15% the size of Google financially. We have some, not quite 200 offices in 70 countries. We run the site in 46 languages. And we offer travel basically to every part of the world that is reachable and interesting for tourism somehow. That's what it looks like. We sell hotel rooms globally. We are part of the Priceline group of companies. That means that Priceline also sells flights, rental cars, sells rental cars, and OpenTable offers restaurant visits. If you integrate all of this more, then we are basically offering everything that is necessary to have a nice vacation or a nice experience in general. So it's kind of moving from hotel rooms to something more trip-shaped and a complete experience. We currently run 3 data centers. These are actually not our data centers. This is rented colo space. It's traditional colo space, so it's Uptime Institute Tier 3 stuff that is available on the market. In that there is some 30K machines, so there we are only about 1% the size of Google, and all of that in way too many configurations. The hardware is mostly HP, Dell, Supermicro, 2-die, E5, Xeon type stuff. Mostly 2620s and 2690s, strangely, because of some of the software that we run that is very dependent on single-threaded high clock performance. We hope to get rid of that sometime, but for the moment we are basically on the both extreme ends of the CPU spectrum that is available from Intel. We are a Rapstores B company, that is, we mostly for money replace variables in HTML templates. That is quite boring thing to do. The data that goes into the variables that go into the templates, that comes from databases. That is also very traditional. We have a pretty large MySQL deployment. We try to keep stuff in memory where possible, so if we see a disk read and anything customer facing, there's probably a bug. It's certainly a problem. We run much more complicated stuff in the background, so we do the usual big data stuff. We have a very limited GPU deployment at the moment that does deep learning, image processing, and fraud detection, and experimental user interfaces, stuff like that. And we have a pretty large-scale data movement infrastructure for MySQL, for Elasticsearch, Cassandra, Hadoop. So all in all, it's not too weird. It's a bit specialized in what we do and how we do it. But it's all, well, we have the source to everything really that earns us money. There is a SAP somewhere, there's a bit Windows in the Office area, but the stuff that earns us money, we can read the source to everything, and we also have the people that understand that and that can debug that. That doesn't mean that we want to change it. We are very much a hotel company and we want to stay that. But sometimes size or problems forces us to actually read that and then talk with the vendors about possible changes and what we need changes and what would be the best way to get that change into everything. So it's all very user-centric actually. We want to stay a hotel company, but size forces us to deal with more of the technology and to get closer to the actual hardware in order to manage that. Growth, we have been growing faster than Moore's Law for a long time. Growth looks like this. Because there are numbers here on the y-axis, I can only show old data, I cannot show recent data, but the shape overall is pretty much the same. These are room nights and hotels available on the source. These are also public numbers in the reports. But the curves for everything else, for machine capacity consumed, for meals served in the canteen, for people hired, for anything really, they look pretty much like that. And they look even more interesting if you put this on a logarithmic y scale, because then they become nice lines. And you can see then where that goes. If you translate that into data center capacity, we have a problem. Because if you see, this is contracted power, that is the actual power draw in one data center. And then if you add capacity here, you can see how that quickly escalates. If you naively draw that line further out, by 2040, we have covered the entire planet in computronium. That is a bit of a problem, because we also need room for the hotels. But that is not going to happen anyway. It underlines the problem, though. We need a change in the way we handle stuff, because if we add capacity like this, this is not going to work anymore. And this has very, very practical implications. Currently, we do a very enterprisey traditional build out. We get space. We do the electrical build out. We add racks, we add switches, we add chassis to the racks, and then we put blades in there. And we need to scale that out better. This is happening in waves, because all of these things have different latency from the time you commit to this actually being finished and useful. And because all of these things happen independently and in waves, they are hard to synchronize, they often go wrong, and then everything is bad and everybody hates infrastructure. Once the hardware is in place, we can then finally automate that, and for that we have a system called ServerDB. I will show a bit more of that later, which basically gives you an API and a web clicky interface where you can get one server or 200 and tell these servers to, for example, become a MySQL database replication chain, and then you will get a mail 20 minutes or 2 hours later that everything is finished and in production. That is actually nice. This way of doing things is pretty attractive, at least to people with a Netherlands background, because it allows you to delay large CapEx expenses as long as possible. So it gives you a lot of flexibility in spending planning and actually delaying the actual stuff happening. With the business with that amount of volatility and growth, it is useful to make a lot of plans with a lot of variables and then commit to them only as late as possible. Commercial data center space, Uptime Institute Tier 3 space, comes with a lot of limitations. If you talk to providers of such space, we end up with a lot of small rooms that then give you a lot of placement constraints. We have a power limit per rack of 7 kilowatt, and this, for example, is a blade center here. If I kick that very hard, it consumes 6,400 watts. So if I don't want to overcommit to power or cooling, I end up with knee-high racks. That is a bit ridiculous. You have problems with build times if you build like this. You actually have trash issues if these things come in individual components, or maybe even the blades individually, and you unpack that in the shared space, the loading and staging area of the data center, then everybody else in the data center is going to hate you quite a lot, because if you get a monthly delivery, that means that for a week that ramp is completely unusable. And the interface we talk to the machinery to get it running is basically the LOM, whatever the vendor is calling it. If the LOM is in any way different or not reliable or slow, we get a lot of hate from everybody because the machines are not coming up properly. Yeah, that's a load test for such 2690 in this case. I have been measuring the power consumption over the number of cores that I keep busy. And if you look at the total power draw here and multiply that with 16, then you end up with a 6.4 kilowatt chassis and a 7 kilowatt rack, and then it's game over. And that is a rack of 40 machines. I got 32 because I had 8 LOM failures during provisioning. These are Hadoop machines, they are 40 core boxes, and I get this 7 kilowatt rack running at 15 kilowatt here, so that is a huge overcommitment into hotspot, and that required additional cooling in this case. Yeah, I have, because the LOM is the thing I use to talk to the box, it's our gateway to automation. We are looking at LOM issues a lot. It's often under-documented, multiple access paths. Which is a problem with auditing if you're trying to document a configuration. Make sure that what you configured in your system is actually what is running. That's really complicated. It's often insecure. It often uses outdated crypto, by default sometimes none. It has insecure client requirements. Some things require a Java console if it's older, and it requires a Java version that I'm not allowed to run on this box because then corporate security is going to hate me. There are different access methods depending on the vendor. There is a partial fix for that. That is Redfix, which is Redfish, which is actually an open compute thing, or being used there quite a lot. There are differences in feature sets, which is less a problem because we are not going to use much functionality from it. We basically use power reset and boot preference, and optionally we're using firmware update and partitioning and controller config facilities. But there are other ways of working around that. As long as there's a command line tool, I can always boot into a RAM disk and then run scripts from the RAM disk to exercise the machine from the inside. So if a simpler, more reliable LOM means I have to do it this way, that is also accessible. And metrics, I use power, temperature, and cooling, and fault sensors. So it's also not a lot, and it's all read-only mostly. So as long as I can power cycle the machine and set the boot preference, I have only read-only controls necessary in the LOM. A simpler LOM that can do less, and that when it does something always interrupts production, is something that is easily audited. And that is something that the corporate security people are going to like a lot as well. So that is useful. That is ServerDB. ServerDB is ugly, but very functional. It's a thing that allows me to view everything we have discovered about the server with the various discovery methods. It gives me an action menu that allows me to do things with the server. It links to the monitoring, to the network provisioning, and the other interfaces we have. So it's very deeply integrated with all the other tools that we have. It shows me the toilet paper roll for the base system metrics. It used to be a single Python app, but that became unwieldy, so it's being refactored very hard now. And it is now mutating into a complex of systems doing network, switch, storage stuff, rack and machine configuration, and it leverages existing tools wherever possible. So a foreman can do a thing. We are not going to keep up our own code for the same purpose, but throwing that away and are integrating external projects into this. This allows us to get rid of a lot of infrastructure management and share the cost of maintaining all that with others. It has a lot of business knowledge. How are we doing things at Booking? And it does full lifecycle management for a server. So everything from actually interfacing with the purchase order system on the front end to getting stuff and decommissioned and out of the data center after several years is managed by this. This is the network view. It's called Nemo, which is the network manager side of ServerDB, if you so wish. It also provides rack views, multi-rack views here, single rack views in this case, also switch metrics, power consumption metrics, and other stuff. And it does that across the entire infrastructure, several data centers, and 10,000s of servers. So it also scales nicely. It's not limited to a single chassis or a single rack. That is where we're coming from, and if you're looking at where we're going to be at the current growth rate, it's pretty clear that what we need to do is we need to go rack scale, so we are not receiving individual chassis or systems anymore. We need to bring the volume up by having fewer configurations that allow greater production runs at the order side to get more favorable conditions there, and of course getting rooms to match the racks that we order. And that actually turned out to be the most important thing, and I'm going to talk about that quite a bit more. But first, let's look at the rack scale thingy. There is actually a way to order blade centers by chassis that actually reduces the trash quite a lot already. It streamlines the late provisioning phase. We get things quicker and pre-assemble. It's helping quite a lot. You're a bit limited in what goes into a chassis, and the chassis we're currently using is going to be discontinued. The reasons for that are legit and pretty okay, but the direction it's going in is not actually what we want. We see the same thing when we look at rack scale systems and if you look at inter-rack scale designs. You can order stuff also by the rack, and then you look at this inter-rack scale design stuff. HP, Dell, Supermicro, they all have their own variation of that, so they take what Intel has in the RSD definition and then value out their own stuff on top of that. That gives you a bit more design flexibility than Datacenter chassis gives you. Depending on the actual physical design, it gives you the same shared power and cooling savings that chassis give you, even at a somewhat larger scale. But it's all pretty weird and proprietary stuff. It has integrated rack management. It comes with pod and rack level controller software, like a Datacenter chassis has a controller. It does, and that's a thing, a lot of composable hardware. So you have PCI switches that allow you to route disks to memory modules, but it does this with PCI buses that basically extend through a chassis or an entire rack. And that means that you have like a second rack scale network topology next to your IP topology that you already have anyway, but it's pretty limited in size and range that you have. And sometimes, if you look at stuff that Dave, for example, promotes, you can get this stuff with a data center wrapped around it. That goes into a weird direction though, because it is looking at shipping container sized thingies that are being used as building blocks. So you are looking at stuff that is built for very high density. You basically have to cram what you want into Legos of 8 by 8 by 40 foot. And then you look at very high wattages inside the rack, and that gives you constraints again in what you can do. It's pretty nice, but it is also a direction that we don't want. We want actually keep the density at the watts per rack at a moderate level, higher than we currently have, but if you go to extremes there, you are looking at expenses and at engineering challenges that do not actually contribute to what we want. So this is even more bespoke, and if you look at Open Compute, that is like well, shipping crates of computers, but ugly. But you only get what you actually need. It's like a JBOD of computers instead of getting a RAID or other integrated system. And the value is then added at higher level software. For the management side, we have that. We have the ServerDB effort, which is going to interface with that. And for the production side, if you want at the workloads running at the machines and want them to be mobile as well, you're looking pretty hard at containers. And that means that you probably also want Kubernetes to slice and dice the machines. They're too big for most application workloads anyway, even the small ones. And you probably don't want to tie your workloads to a single specific bare metal machine anymore. You want it to be able to float around. And that has two requirements. One is the Kubernetes stuff, and the other is the storage disaggregation stuff. So what you get from Open Compute is a clean bare server design without any value add, and that's actually the value add, because it makes the hardware extremely even. And the hardware that is there is documented, so we can integrate it with our own systems. We can actually look into the BMC if it's not working and see why it's not working, or what it expects us to do. And because we can read and write source code, that is, we have potentially a lot fewer problems actually as well. The deliveries by the rack, that is a challenge that we just mastered for the first time. That was 680, 670 kilos approximately coming in. And in a traditional colo where we are, that is actually also borderline of what is possible. So we're probably not going to get Hadoop hardware by the rack, because it will, on the way to the final location, break to the floor somewhere, even with spreader plates. That is not possible. 1.5 tons a piece is not going to happen in that location. Which also means we need to look at locations very hard. And these locations look probably a lot more like we heard in the previous talk here, with concrete floors, no raised floors, everything is flat and even, and then rolling equipment racks into place with no problems. Open Compute comes with a lot of potential operative and capital savings, but in order to unlock those, you actually need to be in a location that allows you to do that. And I'm going to talk about that a bit more as well. But well, getting volume up. This is the provisioning screen of ServerDB. In a location, you have a bunch of server profiles. This is actually, I've counted them, that goes to 11 here. 9 blade types at the moment, and blade 2A, blade 2B, and blade 2 makes it 11. If you look at those, they are basically 2 CPU and 2 memory sizes. So I might be able to get that down to 4. but there's a lot of variation in the storage that differentiates these units. There are often 2 disks or 2 SSDs. We actually want our customers to not rely on that. We want the individual computers to fail, not often, but they should have the very real possibility of failure, so that the consumers build systems that they can reproduce and that can fail over, that forces them to consider that and build systems that run without a single point of failure. I'm looking at the current server-DB statistics, and there are about 500 machines that are pre-Xeon E5s. So they are X and A Xeons. That means they are from 2012 or earlier, and they have either not been provisioned or deprovisioned, or the server-DB has invalid data. But out of the 500 machines, there are slightly over 100 that are labeled in live state. That means they are also in the monitoring automatically. So they're probably productive, and they can't even mitigate meltdown. They have no PCIe, CPU features, and other things. These things need to die, that is hard. They are hard to kill. I mean, if something is running since 2012, even if Puppet is on the box, then nobody knows if that puppetry is actually still going to work with current versions of things. So we need to exercise all that, not too often, but regularly, and keep everything agile, because otherwise we're building up a lot of craft, and then later constraints that prevent us from changing and developing everything. So having the possibility of things going away and failing is actually not a bad thing. It forces people to stay agile and still live with the possibility of change. That is useful. The answer is obvious: ban everything. In this case, we ban local storage. So we build machines with very limited local storage, probably not rated. SSDs don't fail that often anyway, so that's a good thing. We put up a per rack budget of 2 head units, 500 watts and a single 100 gig port on the top of rack switch, and then give that to our storage guys and tell them put something in there, we don't care what, and make it available with iSCSI or NVMe over UDP, Rocky, or other things. These things will interface with each other, build redundancy across the racks, and all the compute will talk to that storage in some way. So we have east-west data access traffic, we have replication traffic, and that all happens on the iPad network, not on some proprietary backend network. We still have machines with fiber channel cards, they all need to die. I'm certainly not building PCI networking next to IP networking here. I'm using my IP network as the transport network for storage as well. IP cables, fiber cables, they are my disk cables now. And I'm telling the network guys to build a leaf and spine infrastructure that actually can carry that without dying. And that can be built out incrementally so that I don't have to spend all of that up front. That gives me pretty uniform production compute here and no local persistence. If you want to keep your data, you put it here. And that takes care of the replication if you want it, or you order storage here as JBots and then do that. If you're Cassandra, you're doing it yourself. If you're doing a MySQL, you're asking this to provide resiliency. But that also gives me workloads here that can migrate from one box to another, because they talk to iSCSI anyway, and probably not to local iSCSI, but somewhere else. So that will work nicely as well. And if I add Kubernetes here, that gives me resiliency, application mobility, and also capacity size adjustment to what the application needs and not what the hardware provides. And in the end, hopefully, if I can get rid of my workload that requires the 2690 CPUs, I can run everything on the very cheap 2620s or silver 41110s and be fine with that. And then I order only one type of rack and be done with it. That day, I will have basically optimized myself out of job, and that is my goal. So 4 profiles or less, disk as requested, location independence, independent hardware upgrade cycles, storage, compute, rack, and all can be upgraded independently. And because I have application mobility, I don't even have to interrupt production when I'm taking out the rack for upgrade. And I have one single network, aggregated 10 gig, 25 gig, or 100 gig. That depends a bit on the data center and the age of the racks to bind all of that together. The only thing that falls a bit out is the Hadoop environment, which is a bit special. But on the other hand, Hadoop is not built for latency, it's built for bandwidth and capacity, so I can actually optimize that even harsher. And in the end, it will kind of fall into the same schema, only if the details look a bit different. That's why it's a separate environment. Getting rooms to match. You have seen these images already. This is a classical Tier 3 Uptime Institute data center. This is an Open Compute optimized data center. These things supposedly can be built much cheaper. We ask and typically are being told for a megabyte of capacity, you are going to spend 10 million for an empty data center shell here. Facebook claims to be able to build this as a shed basically for 2.5 million. If I can get that for 5 million or less, I will be pretty happy with the outcome of that. It will have a better power factor as well, so I will be happy with that as well. And I actually need this cheaper, rougher, hotter data center with hot air containment and a concrete floor and everything from the front, everything from the top, in order to unlock all the power and cooling benefits that Open Compute offers me. And that's a bit of a problem because I'm not getting that. In the Uptime Institute market, in the Tier 3 data center market, I have a two-sided market. I have a market where demand and supply are anonymous. People are building data centers without having the name of a customer on the book. But if I am looking for Open Compute data center space, I probably have to have that built for me. So my name's on the book. That gives me a higher latency because it's not pre-built. And my commitment to using that is also longer because it's now built for me and not general data center space. And the part of the data center project within the Open Compute Foundation is important because this common spec that people build and commit data center space to without having a custom name on the book is the key that unlocks pre-built data centers that match the spec, which are necessary for getting big racks in there that are very heavy and which are also key to unlocking the power and cooling benefits that Open Compute has. So one central part of the Open Compute work is basically this data center team, getting that spec out and getting people to commit to build data center space to that spec and to these conditions in order to actually get the benefits of everything else that you put in there. If you have pre-built data center space, you have it available quickly, you have it available at a higher flexibility, shorter commitment times, and that is the key for smaller business. People like Facebook and Google build data centers multiple at the same time and fill them completely alone. But if you are a smaller customer, if you're smaller than those, then you need that two-sided market for that to take off. That has a bit higher cost, of course, because you're basically paying, when you're paying the rent for the data center, you're paying also part of the risk. If you're our size, you also have capacity fragmentation because half megawatt rooms are not going to cut it. You need too many of them to actually be fun. But for normal sized companies, that is not a problem. So once that market is there, you're basically just ordering rooms from the market and they will be available close to immediately. So 3 months or less. That's the thing. So how does this work on smaller scales? How do you make Open Compute available to smaller companies? Part of it is to look at the rack and the room as a system. You have the rack that is able to run in harsh, hot environments that are less nicely decorated and air-conditioned than traditional data centers. And then you build a data center that is cheaper and cools less and does not have all the power conditioning and stuff. So that with the cheaper data center and the cheaper running costs, you can actually leverage the rougher and tougher Open Compute hardware to have less operating cost of the entire thing. But that means that these two things need to be built for each other, and they feed on each other and on the definitions so that they match. And you need that pre-built, you need the two-sided market. And only then, with this, you will then later leverage the documented machine interface for open integration. That means that people like us or others are going to write provisioning systems that manage the entire life cycle of a data center, not individual racks or data center chassis on a larger scale, to not only utilize it like Kubernetes does it, but also provision it across the years in an automated way. And then you have something that is actually worthwhile and is progress over what we are currently doing. But that requires all the openness and all the specs from the OCP Foundation. That's why we're looking at that. Questions?
What's the max operating power of the temperature? Max operating temperature?
I have been told that these systems will survive 35 or 40 degrees air in. That will then give you 60 degrees air out, and that is why you don't put people in a hot air in a local computer data center. Because then you get mummies out, and then you have a lot of paperwork.
One other question, Chris?
It might be worth pointing out that one of the accelerators for the storage disaggregation is the fact that our server fleet only has two 2.5-inch drive bays per server, which is a lot less than in similar hyperscale environments.
Yeah. So one of the accelerators of the disaggregation is that the space for disk drives in the server is limited in blades as well as in these things. But also we find that the storage space that is in the servers we have is also always over-provisioned. Of course, if the disk full, the server is not serving properly. And with disaggregated storage, you actually cut the volumes to size, so you have also less overhead. And that enables also a much faster transition to SSD where it's not already complete.
Great.
Thank you.
Thank you very much, Chris. All right, we're down to one more, and then